When we define matrix column vector multiplication via dot products, we look at the output of our multiplication as a collection of individual scalar entries. Let's see what we mean by looking at the formal definition. We begin by letting A be an element of Rm by n. This means A is a matrix with m rows and n columns, each of which is a real number. We also let X be an element of Rn by 1, meaning X is a column vector with n rows and 1 columns, each of whose entries is a real number. We define the matrix column vector multiplication A times X equal B. Here, B is the desired output of our product. In this case, B is going to be an element of Rm by 1. In other words, this product, A times X, is going to be a column vector with m rows and 1 columns, each entry of which is a real number. When we define this product using dot products, we take an entry by entry approach. In other words, we look at the output as a series of m individual entries, and we define the ith entry of this dot product using a scalar valued formula. Specifically, b sub I, the ith entry of the output vector b, that of course is going to be equal to entry I comma 1 of A times X. Remember, in the entry notation, we say that this entry is going to be in the ith row and first column of whatever's in the argument. So this bi is the ith entry of A times X. And we define that to be a dot product between the ith row of A, written as a column vector, this is very kind of interesting, dotted with the vector X. We of course can write this in summation notation as k goes from 1 to n, aik times x sub k, which we're going to see in just a minute when we do our analysis. This is true for all I goes from 1 to m. Remember, the output vector has m rows and 1 column, so there are going to be m different scalar outputs that we're going to calculate. And if we do all of those, we're going to get a vector b, which is composed of individual entries b1, b2, all the way down to bm, where each individual entry is written as the following dot product. So the first entry is a11x1 plus a12x2 plus da 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 a1n xn. The second entry is a21x1 plus a22x2 plus da 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 plus a2n xn. And then we go down to the bottom and it's am1x1 plus am2x2 plus da 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 amn xn. Now, of course, when we're exploring the definition, it's not enough just to read the formal definition. That's a good start. What we're really going to do is dissect this and analyze it at a pretty deep level and make connections between this definition and previous work that we did defining matrix column vector multiplication via linear combination. Let's do that now. During the process of breaking down a definition to make sense of what's going on, one of the best ways to do it is actually to write the definition in our own handwriting and expand on each individual part of the definition step by step. In this case, we see that in order to find the matrix column vector multiplication via dot products, we're going to be breaking the entries of A into partitions based on the rows in A, and then we're going to be breaking the actual output vector B based on individual entries. So with that in mind, we could look at the matrix vector product A times X. Let's think about A as broken up into row vectors. Remember that if A is an m by n matrix, let's go ahead and write that. A is an m by n matrix, and then X is an n by 1 vector. We said that the inner dimensions must agree. So the number of columns of A matches the number of rows of X. We're good on that. When we think about the size of the output, the inner dimensions, quote unquote, cancel out. And the output size is going to be m by 1. So this output vector would be an m by 1, meaning that we're going to have m individual entries in that. We can push even further. Remember, this entire matrix that we've cut up into rows is an m by n, which means each individual row is a 1 by n. So each of these things, row 1 is a 1 by n, row 2 is a 1 by n, and then row m of A is a 1 by n. And then, of course, this vector over here is going to be an n by 1 given our definition, and then each one of those is going to be a scalar. We have in our definition that if we want to have the ith entry, we're going to take the ith row, transpose. One of the major questions is, why do we need a transpose there? Let's get into that in just a moment. And then we're going to dot it with the vector x. one of the best places to start to get a sense of this is just set I equal to 1. Holding that in mind, here B1 is going to be the first entry of the vector B, which is going to be A times X. We just saw in the definition we're exploring that that's going to be the first row of A transpose dot product with the vector X. Remember that the first row of A is going to be a 1 by n vector, where it's going to be given by A11, A12, A13, all the way to the last column, which is going to be A1n, meaning that all of the row indices in that row are going to be identical, and what we're going to be doing is shifting over the column indices. So let's remember this. This is going to be the first row of A treated as a column vector. When I put the transpose, this thing is now an n by 1, and X is also an n by 1. The reason this is an n by 1 is A1, the first row of A, is a 1 by n. When I hit it with a transpose, it transforms that row vector into a column vector. And now we see why we use that transpose. Remember, dot products expect the left-hand side and the right-hand side to have identical dimensions, which means when we're thinking about the first row of A dotted with X, this thing has to be a column vector, which is why we have that transpose there. Let's visualize what this means. Now we have a column vector which represents the first row, A11, A12, all the way down to A1n. Here we have the vector X, which is an n by 1, x1, x2, x all the way down to xn. And then remember, when we do the dot product, what we do is we take the corresponding entries, multiply, and then sum the product. So this is going to be a11 times x1, a12 times x2, a1n times xn, where we sum all those up, and that's exactly what we see. a11 times x1 plus a12 times x2 plus plus a1n times xn. Of course, if we wanted to be slick about this, we could use summation notation, which is exactly what we did in the definition, right? This is going to go from k goes from 1 all the way to n. Here I use k because I'm going across the columns. Even though the indices are written this way, only because it's a transpose, what I'm really doing is going across the columns of that first row, and then I multiply each individual entry in column k by the kth entry in vector x, and then I sum those products up, which is exactly what we see here. The reason that this index was 1 had to do with the fact that we're looking at this as the first entry. Let's keep this exploration going to cement our understanding. Here, let's look at the second entry of our output vector b, so we'll call that b2, and of course that is the entry in the second row and first column of our product a times x. We just said that that's going to be the second row of A written as a column vector. So row 2 of A written as a column vector. In other words, take the transpose, dot product with the vector X. Of course, I can't help but get in the habit of analyzing dimensions. X is an n by 1. Row 2 of A is going to be a 1 by n, which means when I transpose it, I'm going to get an n by 1. This must be a dot product because I'm multiplying the vector on the left by the vector on the right, and they have the exact same dimensions. That's exactly what we expect in a dot product. The output of a dot product has to be a scalar, so this is going to be a 1 by 1. Let's go ahead and write this. We said that the second row of A is going to be written in colon notation as A 2 colon, so take the second row and all columns. We'll transpose that, which means we'll treat the second row as a column vector. Again, this is an n by 1, this is an n by 1. Well, what happens when we take a column vector dot a column vector? Remember, this column vector is the second row of A written as a column vector, so this must be A21, A22, all the way down to A2n. Here we have x as x1, x2, all the way down to xn. And what do? We multiply the associated entries and then add the product. So this is going to be A21 times x1 plus A22 times x2 plus all the way down to the bottom A2n times xn. And of course, we could write this using summation notation. Notice we're going across the columns, which means in this class I'm going to always use a k for that. K goes from 1 all the way to n, A2k xk, where the row index on these entries matches the entry number of the particular output vector that we're wanting to find. The moment we have those, we keep going on and on till the break of dawn, and we get to the last entry of our vector, which we call bm. In other words, that is the entry of the product a times x in the mth row and first column. This definition is claiming that we can calculate that as a dot product between column vectors. The column vector on the left is going to be the mth row of A treated as a column vector with a transpose, and then the column vector on the right is going to be an n by 1 vector given by our input x. Once we have that, we could write the row m of A using colon notation. So this is going to be the mth row of A transpose. Here's going to be x. When we write those right next to each other, of course, when we take this dot product, what we do is we multiply those individual entries. So the first one's going to be am1 times x1 plus am2 times x2, all the way down to the bottom. We add amn times xn. In all this work, we've treated the output vector b as individual scalars and then thought about the value of those scalars as coming from a dot product. We can now stack those back together and look at the entire output as one chunk. So b1 was a11 x1 plus a12 x2 all the way to a1n xn. B2 was similarly defined, the second row treated as a column vector, dotted with the vector x. We go all the way down to the bottom, the mth row of the matrix A, dotted with the vector x, and we get Bm. Now that we've done the work to decipher this definition, I want to make explicit connections between the dot product version of matrix column vector multiplication and the linear combination version of matrix column vector multiplication. Specifically, let's take a look at this definition and notice that each of the individual products here are real numbers, which means, of course, they are commutative. We could switch the order. So a11 x1 plus a12 x2 plus all the way down to a1n xn has to be identical to x1 a11 plus x2 a12 plus xn a1n, where that's a continuation for all the values in between. In other words, we've just switched the order that we do the multiplication. The same thing is true for the second one down, right? We can switch the x's and the a's all the way through, and that happens for every individual scalar. This is still the entry by entry view because we're thinking about the individual entries as the functional unit of the vector, but this is where we can actually change our perspective. Notice that when we think about it this way, we can shift from the entry by entry view to the column vector perspective, or what we might call the linear combination perspective, when we recognize that these first entries are not isolated. There's actually a pattern that happens across every single individual entry. Check this out, x1 times a11. x1 times a21, all the way down to x1 times am1. This is an m by 1 vector. Similarly, in the second slot, we have x2 times a12, x2 times a22, all the way down to x2 times am2. Again, this is an m by 1 vector. This individual scalar additions turns into a column vector addition, and we do that all the way down to the nth row, breaking the individual entries into a set of vector additions. So we would call this the entry by entry approach. Another way to say that is it's the scalar approach to construct the product. Here we have the linear combination approach, where we're thinking not about the individual entries, but the entire product as a linear combination of vectors. Of course, if we push a little deeper, we recognize that in each individual entry, we have the exact same scalar, which means we can kind of factor out that scalar, reverse scalar multiplication. So this becomes x1 times the first column of A, plus x2 times the second column of A, plus all the way down to xn times the nth column of A. But this was exactly the linear combination version of matrix vector multiplication, meaning the dot product version of matrix vector multiplication produces the exact same output as the linear combination version. The difference is in the way that we think about the actual operation being performed. In this alternate dot product version of matrix column vector multiplication, we're literally cutting up the output into individual entries, which means that we cut up the matrix into rows, so row 1, row 2, row 3, all the way down to the mth row. And then we take the dot product between the individual rows and the column vector to produce each entry. In the linear combination, we cut the matrix into columns, and then we take scalar multiples times each column and then a vector sum to produce it. The output is identical. The way we think about producing that output is different. The operational unit that we're using to construct our output in the dot product version is a scalar. The operational unit of the matrix used in the linear combination vector is an entire column vector. As we dive deeper into the interconnections between linear algebraic operations and their use in solving systems, we'll see more about these distinctions. For now, it's enough to recognize there are two different versions, and one of the main differences is how we chunk information in each version. That leads me to my community challenge of today. Could you imagine a row vector matrix operation that is analogous to this. So instead of multiplying a matrix by a column vector using dot products, what if I multiplied a row vector by a matrix and I wanted to use dot product to produce an output? We'll see the answer to that in a future video. Next video, we're going to take a look at this in practice for a concrete example. I'll see you in that video.